Damage Mechanism Review, DMR, for risk-based inspection, evaluating damage causes to enhance inspection strategies. Introduction to Damage Mechanism Review, definition, purpose, and importance of DMR. A damage mechanism review, DMR, is a structured and systematic process used within risk-based inspection, RBI, frameworks to identify credible damage mechanisms, estimate corrosion or deterioration rates, and determine how equipment may fail during service. The primary purpose of a DMR is to provide technically sound input for estimating the probability of failure, POF, which is a critical element in RBI decision-making. By understanding how and why degradation occurs, organizations can move away from generic inspection intervals toward targeted, risk-informed inspection strategies. DMR considers not only internal process conditions such as temperature, pressure, and fluid composition, but also external environmental influences including humidity, rainfall, insulation conditions, and proximity to corrosive atmospheres such as marine environments. The review also evaluates damage modes, such as thinning, pitting, or cracking, and links them to potential failure modes like leak before break or sudden rupture. This linkage is important because failure modes can influence both safety outcomes and consequence of failure, COF. The quality of the DMR directly affects the reliability of the overall RBI assessment, as incorrect or incomplete identification of damage mechanisms can lead to underestimated risks or unnecessary inspections. A well-executed DMR supports safer operations, improved asset integrity, optimized inspection resources, and reduced unplanned outages. It also creates a shared technical understanding between corrosion specialists, inspection engineers, process engineers, and operations personnel, ensuring that equipment degradation is managed proactively rather than reactively. Identifying damage mechanisms, deterioration rates, and susceptibility. Identifying damage mechanisms is the core technical activity of a damage mechanism review. This process requires evaluating the interaction between materials of construction, process conditions, operating history, and both internal and external environments. Common damage mechanisms include general corrosion, localized corrosion such as pitting, erosion corrosion, stress corrosion cracking, and environmentally assisted cracking. For mechanisms such as wall thinning, deterioration can often be quantified as a corrosion rate, typically expressed in millimeters per year or mils per year. These rates may be derived from inspection data, laboratory testing, or operating experience with similar equipment. However, for mechanisms where the rate cannot be reliably measured, such as stress corrosion cracking, susceptibility is used instead. Susceptibility is usually classified qualitatively as high, medium, or low based on known relationships between material properties and environmental conditions. Industry references such as API 571 provide valuable guidance on expected damage mechanisms and influencing factors. Grouping equipment with similar materials and exposure conditions into corrosion systems, as described in API 970, allows inspection findings from one item to inform assessments of other similar components. This approach improves consistency and efficiency but requires careful validation. It is also important to recognize that deterioration rates may change over time. Some mechanisms are self-limiting, while others may accelerate or transition into different damage mechanisms. Therefore, a comprehensive DMR must consider cumulative damage effects and uncertainty, using conservative assumptions when data quality is limited. Damage Mechanism Review Documentation, Integrity Operating Windows, and Keys to Success. The outcomes of a damage mechanism review must be clearly documented to ensure transparency, traceability, and effective use within the RBI process. Typical DMR documentation includes a description of each component or corrosion system, process conditions such as operating temperature and pressure, materials of construction including liners and coatings, fabrication details, identified corrosion types, estimated corrosion or deterioration rates, credible damage mechanisms, susceptibility rankings, and inspection history highlights. When equipment is grouped into corrosion systems, this information should be summarized at the system level while retaining the ability to trace conclusions back to individual components. DMR activities are closely linked to the development of integrity operating windows, IOWs, which define acceptable operating limits for parameters that influence degradation, such as temperature, flow velocity, pH, and chemical injection rates. Operating outside these limits can significantly accelerate damage mechanisms and increase risk. Successful DMR implementation depends on identifying all credible damage mechanisms, ruling out inactive ones, defining failure modes, understanding the consequences of exceeding IOWs, and using methodologies or software tools that comprehensively address known degradation mechanisms. Multidisciplinary collaboration is essential, as process engineers and operations personnel provide practical insight into operating variability, while corrosion and inspection specialists contribute technical expertise. When executed effectively, DMR becomes a powerful tool for proactive integrity management, supporting safe, reliable, and cost-effective plant operation.